We've looked at the probability of individual events, and we've looked at counting multiple events occurring. If we put the two together, we get something called the multiplication rule. The probability that two events will occur in sequence is just multiplying their probabilities. So the probability that both A and B will occur is equal to the probability of A times the probability of B given A, because of course if A influences the probability of B, we have to take that into account. Now if the two events are independent and the probability of A doesn't influence the next event B, then the rule would just simplify to probability of A times probability of B. So let's first look at a situation where the two events are independent. We have rolling a dice and getting 4 5s in a row. So I'm rolling a 5, and then a 5, and then a 5, and then a 5. So what's the probability that I'm going to roll 5 and a 5 and a 5 and another 5? Well, if I roll the first 5, it would be a 1 out of 6 probability of getting a 5. The second 5, it doesn't matter what I rolled the first time. I still have a 1 out of 6 chance of getting a 5. So this is a case where I'm just multiplying their probabilities without changing anything because it doesn't change from roll to roll. These are independent events. If I did one, this turns out to be 1 over 6 to the 4th, which is 0.00077. So highly unlikely, less than a 1% chance, less than a 1 out of 100. It's more like a less than 1 out of 1,000 chance that I'm going to roll 5 4s in a row, or 4 5s in a row, sorry, 4 5s in a row. Now, if I'm looking at a deck of cards, and let's say I'm drawing 4 cards out of a deck of cards, but I'm not putting them back in between, that's a little bit different situation. So what's the probability that I get a 5 and a 5 and a 5 and a 5 from a deck of cards? Well, the first 5, notice, and if you're not familiar with a deck of cards, there's the numbers ace, there's aces, which are A's here, they're called aces, 2, 3, 4, 5, and there's supposed to be 6s under here, but they kind of slipped under here. 7, 8, 9, 10, jack, queens, and kings. There's 13 different values on the card and 4 different suits for a total of 52 cards. So the chances of drawing a 5, there's 4 5s, there would be, so here's my 4 5s here, would be 4 out of 52, or about, let's see, 4 out of 52 for drawing the first 5, because I'm trying to draw 4 5s in a row. So let's say I draw a 5, all right? Oops, I draw a 5, I was going to check that off. So I drew a 5. Now, how many 5s are there left for the next try? Well, there's only 3 5s left. I've already taken this card out, so there's only 51 cards left. This is a case of conditional probability. The probability of drawing a 5, given that I've already drawn a 5, is now 3 out of 51 instead of 4 out of 52. Now I've drawn another 5. So how many 5s are left? There's only 2 left and only 50 cards left. I draw another 5, there's only 1 5 left, and there's only 49 cards left. So to calculate the probability of drawing 4 5s in a row from a deck of cards, I have to do this process. This turns out to be 0.0000369 Very, very small chance of drawing 4 5s in a row in a deck of cards. Now, what's the probability of not drawing any 5s in 4 draws? Well, this would be the opposite. In other words, I could have, I could draw 40, there's 48 different possible ways to get a card that's not a 5. So I could do 48 out of 52. And then I could do 47. Then after I've drawn a card, so I draw any other card, there's only 47 cards left that are not 5s. And there's only 51 cards left. So I draw another card that's not a 5. So there's 46 cards left that are not 5s and only 50 cards left to draw from. And then I've drawn 3 cards that are not 5s. So there's only 45 cards left that are not 5s and only 49 cards altogether. This turns out to be 0.7187. Now notice the probability of not drawing any 5s in 4 draws is not the opposite exactly of drawing 4 5s, because these two would have to add up to 100% and they don't. We'll talk more about that in just a moment. Now, what's the probability of drawing at least 1 5 in 4 draws? Ooh, this one's a tricky one. Drawing at least 1 5 in 4 draws. So let's think that through. Drawing at least 1 5 means I could draw 1 5, or I could draw 2 out of 4, or I could draw 3 out of 4, or I could draw 4 out of 4. And I could draw them in all different orders. So I could draw, like if I'm drawing 1 out of 4, I could draw 3 cards that aren't 5s and draw the 5 last. Or I could draw the 5 first. Or I could draw the 5 on the second card or on the third card. There's 4 different ways I could draw 1 out of 5. 2 out of 5 gets more complicated. I could draw the first 2 could be 5s, the first and the third, the first and the fourth, the second and the third, the second and the fourth, or the third and the fourth. There's 6 different ways to draw 2 5s out of in 4 draws. So when we calculate this at least 1, we're going to think about something called the complement. Remember, the complement was the opposite of a probability, was getting the opposite probability. In other words, 1 minus the probability. So what we need to think of is, what's the opposite of getting at least 1? What is the only thing we're not including when we say at least 1? Well, we're not including none. Okay, no 5s at all. So this is equal to 1 minus the probability of no or none of the 4 cards are 5s. Okay, so we just calculated that. The probability of not drawing any 5s in 4 draws, we did that in number 3. So the probability of at least 1 5 is equal to 1 minus 0.7187, which would equal, let's see here, 0.2812. About 28% of the time, you would draw at least 1 5. Compare that to drawing 4 5s, which is a very, very small, almost 0% chance of that happening. But a 28% chance of getting at least 1 in 4 cards that are 5s. So the two things that are opposite of each other are not drawing any and drawing at least 1. Those are opposites of each other, which is kind of interesting. Now, what's the probability of drawing 2 kings and 2 queens? Okay, so let's go through the same process. You might want to pause and try this one yourself. So I'm going to write king and king and queen and queen. So think about the probability of drawing your first king. Well, there's 4 kings and there's 52 cards. So let's say I've drawn a king now. I'll just cross out my king up here, draw us out a king. So on the second try, I want to draw a king again. Well, there's only 3 possible kings left, but there's only 51 cards. Now I want to draw a queen. Okay, so I've drawn 2 kings. I've only gotten down to 50 cards, but I still have 4 queens left. So this is back to 4, but there's only 50 cards to draw from. Now that I've drawn a queen, there's only 3 queens left, and there's only 48 cards left. Okay, so this would be a little easier than drawing 4 5s. There's a higher chance of this. Not a lot higher chance. This is 0.00002216. So this is not a lot higher chance, but a little bit higher chance. Now, let's look at some other ways to do conditional. Actually, before we move on to this, I want to say that this formula for finding conditional probabilities is more of a concept that I'd like you to know rather than a formula I want you to use. As soon as you start trying to plug numbers into formulas for probabilities rather than just thinking it through yourself, you're going to run into trouble, because probability formulas are notoriously tricky to implement. Because sometimes it depends on how you're computing probabilities, what's best to use. In this case, it was best for me just to think about the cards and how many I had and how many were left. On the first page of the 3.2 notes, it was easiest just to look at the table and read numbers off the table. So we're going to look at another way to look at conditional probability. So here we have a Venn diagram. In a Venn diagram, we have different groups, and when one group is completely inside the other, that means all of these, for example, these are adults in the U.S. These are adults who think government is broken. They are a subset of all of the adults in the U.S. And this is adults who think the government can be fixed is a subset of the adults who think government is broken. So in this outside edge here are the adults that think government is broken but can't be fixed. And these are adults that are out here are adults that don't think the government is broken. Okay, so we can put people in categories based on these circles. So it says, according to a survey, 86% of American adults, that's interesting, 86% of American adults in the United States, I just repeated myself a lot. How about 86% of adults in the United States, there we go, think that the U.S. government system is broken. So we're going to call that B. So we're going to say probability of B is equal to 0.86. Of these 86%, another way we could think of that is given that they think the government is broken. So this is, when you see this is a given. Given that they think the government is broken, about 8 of the 10 think the government can be fixed. So this is the probability that they think the government can be fixed, given that they think the government is broken. And this is 8 out of 10, or 0.8. Now, how do we look at this diagram and think about what these numbers mean? Okay, so this circle, this big circle, represents 86% of American adults. So I'm just going to draw, so this whole circle here is 0.86. So 86% or 0.86. Okay, why don't I just write 86%? That kind of makes more sense when we're looking at the drawing. So 86% of the American adults think the government is broken. So we could, so that's kind of our first thing. Now, is this percent 80% in this circle? So what is the probability that they think the government is fixed, given that it can be broken, is 80%. So is this 80% of all American adults? No, it's not. So let's talk about this. Find the probability that a randomly selected adult thinks the U.S. government is broken and thinks the government can be fixed. So this is one of those cases where we have to think about what are we doing with the probabilities. This is actually one where this probability formula at the top comes in handy. We can say the probability of that the U.S. adult thinks the government is broken and thinks the government can be fixed is equal to the probability that they think the government is broken times the probability that they think the government can be fixed, given that they think it's broken in the first place. Because the people who think the government is fixed, can be fixed, given that they think it's broken, there's a conditional probability here. The probability that people think the government is fixed is based on the fact that they already think it's broken. All right. So we have those two numbers, which is 0.86 times 0.8, and that turns out to be 0.688, or about 68.8%. So it turns out that the group that thinks the government is broken and it can be fixed is this group right here. This is the 68.8%. So that means there's a group that is in between, that they think the government's broken, but they don't think it's going to be fixed. And there's also a group that doesn't think it's broken at all. So given that a randomly selected adult thinks the government is broken, so we got that given B part again, find the probability that he or she does not think the government can be fixed. So we're saying the probability of that they think the government cannot be fixed, not F, given B. Or we could say probability of F complement given B. So if 8 out of 10 of the people who think the government is broken think it can be fixed, what percentage or what fraction thinks it can't be fixed? Well, that's going to be the 2 out of 10. 2 out of 10. So 2 out of every 10 people who think the government can be broken, or 20% of them, think the government cannot be fixed. So once again, is this number in here 20%? No. This is 20% of the 86%. So we could actually come up with some numbers. This is 68.8%. This whole circle is 86.6. So if we did 20% of 86, 0.2 times 0.86. So here we did 0.8 times 0.86. If we did 0.2 times 0.86, we would get 0.172. So that would be the part that fits in this little area right here. So we have 86% are in the big blue circle, 68.8% are in the little red circle, which is within the blue circle, and then 17.2% are in the part of the blue circle that is not in the red circle. So who doesn't think the government is broken at all? Well, that would be whatever's left over outside of the circle, which would be the other 14%. So there'd be 14% out here that don't think the government's broken at all. The last question is, would it be unusual for a randomly selected adult to think that the U.S. government is broken and that the government can be fixed? Okay, so let's go back to where we looked at that. So we haven't actually calculated that, and that the government can be fixed. Oh yeah, we did, right here in Part A. So in Part A, says that 68% of U.S. adults think the government is broken and can be fixed. Would that be unusual to find a randomly selected adult that believed that? No, 68% is a fairly high percentage. So it would not be unusual to find an adult in that category. Should have underlined not rather than be. It would not be unusual to randomly select an adult in that category. Adult in that category. Now, what would be considered unusual? So, rule of thumb. Rule of thumb, and this is the word unusual, you might want to circle that. Events with a probability less than 5% are considered unusual. Oh, I don't know why I put a question mark there. That's a statement. Rule of thumb, events with a probability less than 5% are considered unusual.